In the previous modules, we have learned how to use dummy variables as predictor variables and how we can introduce them in a regression model. When we say a dummy regression variable, what we mean is the variable does not take continuous values but takes different values for different categories. For example, it can take values 0 and 1 for two separate categories. Now, we have seen in the previous modules how we can include a dummy variable into the model and how the introduction of a dummy variable in a model affects the setup of the regression model. In this module, we will discuss the inclusion of a dummy variable in addition to multiple number of continuous regression variables. And also, we will see how the inclusion of a dummy variable will affect the estimates of the slope and the intercept parameters in the regression model. So, previously in a module titled Regression with Dummy Variables 1, we had seen how we can introduce a dummy variable into our regression model, and we had also looked at the interpretations of the regression models which now change due to the addition of a dummy variable into the model. When we say dummy variable, we mean that one or more of the predictor variables are now categorical instead of being continuous. In this module, we will discuss how we can introduce a dummy variable which has multiple categories and not just two, and we will also look at the interpretations of interaction terms between a continuous predictor variable and a dummy variable. So, what are the use and interpretation of dummy variables? Dummy variables are where the variable takes only one of two values, are very useful in econometrics because oftentimes the variables are quantitative rather than being qualitative. In general, dummy variables help in splitting the sample into two groups. When we have a dummy variable which takes two possible values, which is a dichotomous variable, then it helps us split our sample into two groups. For example, male and female, or divides the group into those who voted and those who did not, and so on. In such cases, we code our dummy variable accordingly. For example, if the dummy variable is denoted by D, we have D equals 1 for male and 0 for female, or we can code it as D equals 1 for individuals who have voted and equals 0 for when the individual has not voted. So, let us look at an example here. Suppose our aim is to answer the following question: do female employees earn less than male employees? In this study, we will use experience in years of employment as a continuous predictor variable in addition to the dummy variable in the model. So, the response here we are looking at is wage. Thus, the model can be written as wage, which is our dependent variable, equals beta naught plus beta 1 female plus beta 2 experience. Now, in order to model the above mentioned data, we will define a dummy variable which can only take two possible values, 0 and 1. So, in case regression analysis, we can add an independent variable as a dummy variable and there would be no problem. However, for a binary variable coded differently, we cannot perform the regression analysis in the same way. So, when we have a regression model which has one continuous predictor variable, then including another predictor variable which is also continuous would only add an additional regression coefficient in the model. However, the interpretation of the regression coefficients remain the same as that for one regression parameter. But when we want to include a dummy variable into our regression model, then the interpretation of the corresponding regression analysis changes. So, in our example, we will code the dummy variable D as 0 for female and 1 for male. So, let us now write down the regression model in terms of our continuous predictor variable xi and the dummy variable di. So, the model is given by yi hat equals alpha hat plus beta hat di plus gamma hat xi, where di is the dummy variable which is 1 for male and 0 for female. Thus, for male, when d equals 1, the equation stands as yi hat equals alpha hat plus beta hat. This is our intercept term, and we have the slope term given by gamma hat times xi. And for female, when di equals 0, then the regression equation is of the form yi hat equals alpha hat plus gamma hat xi. And there is no difference in the slope between the two regression equations. However, because of the dummy variable, when included in the model, there is a difference in intercept between the two regression models, which means the effect of gender of the employee actually changes the regression equation by the term beta hat. So when we fit a regression equation, then our motivation for including a qualitative explanatory variable is same as for an additional quantitative explanatory variable. So in case of dummy variable, which is mostly used when the predictor variable is qualitative, then inclusion of such a variable has the same motivation as inclusion of an quantitative variable. But if we look at the figure on the next slide, the within gender regression of wage on years of experience, they are parallel, and they are parallel because, and being parallel, it is indicative of additive effects of years of experience and gender on the wage. The parallel linear regression equation implies that the slope of the two regression equations are equal. However, as we have seen on the previous slide, the intercept term changes. Initially for female we had intercept alpha hat, and for male we had intercept alpha hat plus beta hat. So the added term in the intercept gives us the second regression equation, which has the same slope and hence parallel to the previous one, but it has moved by the quantity beta hat along the intercept. So when we fit a regression equation, then our motivation for including a qualitative explanatory variable is same as for an additional quantitative explanatory variable. So in case of dummy variable, which is mostly used when the predictor variable is qualitative, then inclusion of such a variable has the same motivation as inclusion of an quantitative variable. But if we look at the figure on the next slide, the within gender regression of wage on years of experience, they are parallel, and they are parallel because, and being parallel, it is indicative of additive effects of years of experience and gender on the wage. The parallel linear regression equation implies that the slope of the two regression equations are equal. And here we can also see the R output, which gives us the corresponding parameter estimates for experience, which is our continuous predictor variable, and the corresponding estimate for the regression coefficient corresponding to our dummy variable, which has been written as female. And as we can see, both the continuous variable and the dummy variable, which have been used as predictor in the model, they are both statistically significant, and we can draw this conclusion from the corresponding p-value for both the estimates of the regression coefficients. Now suppose we have a polytomous dummy variable. What do we mean by polytomous? In the previous example, we had talked about the dummy variable which takes two possible values, one for male and 0 for female. There could be a situation where other than male and female, there could be different categories, and the dummy variable could be used to categorize all of them. For example, let us consider the regression of the rated prestige of occupations on the income and education level. So income and education level here, these are the continuous variables, and we wish to regress rated prestige of occupation on these two predictor variables. So let us classify the occupations into three categories. The first is professional and managerial, the second is white collar, and the third is blue collar. The three category classification can then be represented in the regression equation by the inclusion of a dummy variable, which is coded as follows. So for category blue collar, the variable D2 takes value 0, it takes value 1 when it's white collar, and it takes value 0 for professional and managerial. And in case of variable D3, 3, which is also a dummy variable, that is coded as follows. It takes the value 0 for blue collar, takes the value 0 for white collar, and 1 for professional and managerial. As you have seen here, for blue collar, both the values of D2 and D3 are 0. This has been taken as a baseline category. And this is the common practice when we have more than 2 categories. One of the categories is considered the baseline, which is considered to have value 0 in case of all dummy variables, and based on that we categorize the remaining categories. So the regression model can then be written as yi equals alpha plus beta 1 xi1 plus beta 2 xi2 plus gamma 2 di2 plus gamma 3 di3 plus epsilon I, where x1 is income and x2 is education, the 2 continuous predictor variables that we had included in the study. So this model describes 3 parallel regression planes which can differ in their intercepts. As we have seen before, inclusion of dummy variable without interaction term usually gives us parallel regression lines where the slopes of the regression lines are equal, but the intercept changes from the inclusion of one dummy variable to another. So in case of blue collar, we have the regression equation yi equals alpha plus beta 1 xi1 plus beta 2 xi2 plus epsilon I, because both D2 and D3 have taken the values 0. For white collar, yi equals alpha plus gamma 2, which is the new intercept, and plus beta 1 xi1 plus beta 2 xi2 plus epsilon I. Similarly, for professionals and managerial position, we have yi equals alpha plus gamma 3, which is now the new intercept, plus beta 1 xi1 plus beta 2 xi2 plus epsilon I. Alpha in the first model gives the intercept of blue collar occupations. Gamma 2 represents the constant vertical distance between the regression planes of white collar and blue collar, which is the difference in the intercept of the 2 model. Similarly, gamma 3 represents the constant distance between the 2 planes. So blue collar occupations are coded 0 for both dummy variables. So blue collar serves as the baseline category. On the next slide, you will see here the plot of the 3 planes which are parallel to each other, and the plot also shows us, the diagram shows us the distance between the planes, which is equals the difference in the intercept of the 3 models. So the choice of a baseline category, where the baseline in this example has been used as blue collar, it is usually arbitrary, for we would fit the same 3 regression planes regarding of which of the 3 categories is selected for this role. So no matter which category is selected as the baseline, we would end up fitting the same 3 regression planes which are parallel to each other, differing only in the values of their intercept. So because the choice of baseline is arbitrary, we want to test the null hypothesis that no partial effect of occupational type exists. So when we fit this regression model using the 2 dummy variables D2 and D3, the null hypothesis of interest is that gamma 2 equals gamma 3 equals 0. But the individual hypotheses gamma 2 equals 0 and gamma 3 equals 0 are of less interest. So the hypothesis gamma 2 equals gamma 3 equals 0, this can be tested by the incremental sum of squares approach, where we remove both D2 and D3 from the model and test the statistical significance of this model, and then include them and look at their corresponding p-values for the estimates and decide on whether the inclusion of these 2 dummy variables was statistically significant or not. Similarly, if we generalize the inclusion of a polytomous explanatory variable with m categories, then we code m-1 dummy regressors. And as you have seen in the previous example, we had 3 categories, one of which was considered the baseline. So we had 2 dummy regressors. In general, when there are m categories, one of them again is considered as the baseline, and it is chosen arbitrarily, and we have to code m-1 dummy regressors. So one simple scheme is to select the first category as the baseline. Since the choice of the baseline is arbitrary, In practice, we usually start with the first category and consider it as the baseline and continue coding the other variables. And when observation I falls in category J and 0 otherwise and takes the value 1, so the m-1 dummy regressors are coded as follows: dij equals 1 when observation I falls in category J and takes the value 0 otherwise, where I and J both run from 1 to m-1. And to test this hypothesis that the effects of a qualitative explanatory variables are not significant, we delete its dummy regressors from the model and compute the incremental f-test. Now, we have talked about dummy variables. We have talked about models that have dichotomous dummy variables and also polytomous dummy variables. But in either of these cases, we have not considered an interaction term between the dummy variable and the quantitative variable that is present in the model. But we would also like to look at the modeling of interaction terms when they are present. So, two explanatory variables interact in determining a response variable. When we consider two predictor variables, under certain circumstances, there are cases where the two predictor variables also interact among themselves and their interaction also has a separate effect on the response variable or on the dependent variable. So, when the partial effect of one depends on the value of the other, there is an interaction effect on the response variable. The models that we have considered so far were additive, and additive models specify the absence of interactions. If the regression in different categories of a qualitative explanatory variable are not parallel, then the qualitative explanatory variable interacts with one or more of the quantitative explanatory variables. In the previous example, we have seen the three planes that only differed in the value of intercept, and they had the same slope, which gave us the parallel planes. But when there is interaction between the dummy variable and the continuous predictor variable, the planes would not be parallel anymore because there will be a change in the slope. So, consider the hypothetical data and contrast examples with shown in figure on the next slide, where the effects of gender and education were effective. In A, gender and education are independent, since women and men have identical education distributions, and that can be clearly seen from the figure. However, in B, it shows that gender and education are related, since women on average have higher levels of education than men, and this again is very clear from the model that we have fitted and the figure on the next slide. In both A and B, the within gender regressions of income on education are not parallel. The slope for men is larger than the slope for women. And why is that? This is because the effect of education varies by gender, education, and gender and education interaction. It is also the case that the effect of gender varies by education. Because the regressions are not parallel, the relative income advantage of men changes with education. So, these examples illustrate another important point, and this important point is that interaction and correlation of explanatory variables are empirically and logically distinct phenomena. Two explanatory variables can interact whether or not they are related to one another statistically. Interaction refers to the manner in which the explanatory variables combine to affect a response variable, not to the relationship between the explanatory variables themselves. So, how do we construct interaction in a regression model? So, we could model the data in the example by fitting separate regression of income on education for women and men. We can consider two separate models, one for men and the other for women, and we can fit these regression of income on education. But a combined model always is helpful to test gender by education interaction. However, a properly formulated unified model that permits different intercepts and slopes in the two groups produces the same fit to the data as fitting two separate regression models to the data set. So, let us consider the following model which accommodates different intercepts and slope for men and women all put together in one model, which is written as yi equals alpha plus beta xi plus gamma di plus delta xi di plus epsilon I. So, along with the dummy regressor D for gender and the quantitative regressor X for education, we now have an added term which is the interaction regressor X times D. So, the interaction regressor is the product of the two regressors considered in this model, but it is no longer linear and thus it is not an additive model anymore. So, for women, when di equals 0, the model stands as yi equals alpha plus beta xi plus epsilon I, and for men yi equals alpha plus gamma, this is the new intercept term, plus beta plus delta, which is the new slope term, times xi plus epsilon I. So, these regression equations are graphed on the plot in next slide. Alpha and beta here are the intercept and slope for the regression of income on education among women, and gamma gives the difference in intercept between the male and female groups. Delta gives the difference in slope between the two groups. So, if you look at the plot on the next slide, you will see that the two regression equations, one with intercept alpha and the other with intercept alpha plus gamma, are separate at the intercept level by the amount gamma, and also the slope of these two models have also a difference of delta, which has been reflected in the difference in slope. Now, how do we test for interaction? When we wish to test for interaction, we wish to test the null hypothesis whether the change in slope, which is delta, is significantly different from 0 or not. In the additive no interaction model, gamma represented the unique partial effect of gender, while slope beta represented the unique partial effect on education. However, in the interaction model, gamma is no longer interpretable as the unquantified income difference between man and women. So, extension to polytomous factor is a straightforward method from here on, and we will discuss it in a separate module. In this module, we have learned how we can include a dummy variable in a regression model which contains other predictor variables which are continuous. We have seen how we can introduce a dummy variable with more than two categories in a regression model, and also we have learned how we can include interaction terms between the continuous predictor variables and the dummy predictor variables. And all these regression models have been illustrated using output from fitting regression model in R.